Okay, let's say we need to find the slope of this line. Okay, so to find the slope we need 2 points. So let's say the first point is here, the second point is right here. Alright, now to find the slope we usually need coordinates. Now we're not going to actually have values here, so let's just call this x1, whatever this value is, and this would be y1, right? The y-axis, the x-axis. Over here at this coordinate here, this would be x2, this would be y2. So the coordinates for this point, we have x1, y1. Over here we have x sub 2, y sub 2, which we're all familiar with. And to find the slope, we know the slope formula, m is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1, right? And this gives us our slope, right? The slope of this line, right? Now you need to understand that slope is the same thing as average rate of change. Average rate of change. So and any question that asks you to find the average rate of change, they're just asking you to find the slope, right? So find your x1 and y1 values, x2 and y2 values, and just plug it into the slope formula. Okay, so slope is the average rate of change, right? So now let's explore another idea. Let's say we need to find the slope of a line, right? So we need to find the slope of a line tangent, right, tangent to a curve. For example, right here we have, oops, I'm sorry. So right here we have this curve right here, and this line is tangent to this curve at this one point, right? So we need to find the slope of this tangent line. So we're trying to find the slope of the tangent line. Well, the problem is, in order to find slope, you need 2 points. Okay, you need 2 points. Well, we don't have 2 points. Right? We don't have 2 points. All we have is this 1 point, right, on this tangent line. So how do we go about finding the slope of this tangent line? Well, what you do is, let me draw another point. Okay. So here's the same tangent line. Right, so here's the same tangent line right here. So here's the point that's tangent to this curve. So let's say there's another point, right, on this curve, and I'm gonna draw a line going through this point and this point. So this line, there's a name for it. It is called a secant line. All right, so this line here is a secant. Right, this is a secant line. This is a tangent over here. This is a secant, and the whole point of this is, well, if I start taking these values, right, let's call this P, this point P, and this is point Q. If I start taking point Q and I start moving it closer and closer and closer and closer and closer to point P, eventually, all right, what's going to happen is it'll become the same line, which is the tangent line, correct? So if I take this point Q and I start moving it closer and closer and closer, so this line, right, this secant line is going to start moving. And eventually, as this gets really, really close to P, right, really, really close to P, basically it'll be the tangent line. So that's the whole idea of this right now, okay? So to represent that, let me show you a diagram, right? So as we start taking it, so here's point P, here's point Q. So as we start taking Q and we start moving closer and closer, you notice the secant line here, it starts to be looking more and more, right? So think of the slope, think of the slope of this line. So as we start moving Q closer to P, all right, so the secant line starts, all right, becoming, all right, very similar, all right, to the tangent line. And then when we get very, very close to P, right, basically it'll be the same line. That's the idea. So as Q approaches P, right, it gets really, really, really close to P, all right, the secant line will basically become the tangent line. Okay, so keep that idea in mind as we talk about the next the next concept, as I bring up the next idea. Okay, so let's talk about the slope of a tangent line to a curve. Okay, so we have a curve here, right, represented by some function, and here's the tangent line to the curve, right? So let's say it's tangent at point P right here. Okay, point P. Now, the problem for us here is we can't find the slope unless we have 2 points. Okay, unless we have 2 points. We only have 1 point, so how are you going to find the slope of this line if you only have 1 point? Okay, well, let's introduce another point. Let's say on the curve, point Q. Okay, point Q. So the idea is this. Let me draw a secant, alright, using the green line. Let me draw a secant through the 2 points. Now, okay, now we can find the line of this secant line right here. Okay, so this is the secant line right here. Alright, secant, spell it out a little bit better. This is the secant line, right? This is the tangent line. Now we can find the slope of this secant line right here because we have 2 points. Okay, so if we were to find the slope of the secant line, let's just say this x coordinate here. Let's say this is x. Okay, let's say over here the y value, right, according to this x right here. Let's just call this f of x. Okay, typically it would be y, right? So let's just call, so the coordinates of point P would be x and f of x. Okay, so typically this would be y, but since we're speaking in terms of functions, let's just call this f of x. And remember, we always replace f of x with y in algebra. Now the coordinates for Q, let's see right here. So Q, if we go straight down, we're talking about right here. All right. Now let's say this distance here, right? Let's say this distance right here from x to this point right here. Let's just say this distance is h, right? So right here, this would be x plus h. So right here, this would be x plus h. Okay, x plus h. So going up the y-axis, we'll just call this right now f of x plus h. Okay. So the coordinates for Q would be x plus h and f of x plus h. Okay, so these are the coordinates for Q. Right, the coordinates for Q right here. So if we were to find the slope of the secant line, right, this is kind of like, this is your x1, y1, your x2, y2. We would just plug this into the slope formula, right? We would just plug this into the slope formula. Okay, so the slope formula, so we're finding the slope of the secant line. It would be, so this is our second one. Here's our y2. Minus our y1 all over we have x2 minus x1, which is x. Okay, now if we were to simplify this, right, we would end up with f x plus h minus f of x all over x, and the minus x cancel, so we get h, right? So we get h. And you notice this is the difference quotient, right? So like we were talking about before, the slope, right, the slope of a line, right, the slope formula, y2 minus y1 over x2 minus x1, that is basically the equivalent, right, to the difference quotient. Those two are the same thing, all right? So the slope of the secant line we have right here. So now we're going to make a jump, right? So how do we go from the slope of the secant line to the slope of the tangent line? Well, as we talked about earlier, if we take point Q and we start moving it closer and 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 closer to point P, right? As close as possible, like really, 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 really close. But it never equals point P. We can't have it equal point P, right? Because if P and Q are equal, right, when we subtract, right, what happens is we're going to end up with 0 in the denominator, okay? So the x values of P and Q cannot be equal, but we're going to take Q and we're going to move it really, really, really close. And as we move it really, really close, this secant line, all right, is going to start becoming, all right, very similar to the tangent line. All right, as you start moving this, point Q down, all right, it's going to basically become the tangent line as we get really, really close to point P. All right. Now look at what happens when Q gets closer to P. That means the distance right here of H starts decreasing, right? Like for example, if I put Q right here, right, the distance for H decreased. So as Q starts getting closer and closer and closer and closer and closer to P, H starts approaching basically 0. All right. So this is how we're gonna make the jump, right? So what did we learn recently about approaching a number, or getting really, 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 really close to a number? What was that called? That was called the limit. Okay. So what happens is if we take the limit of this right here, right? So if we say, so to find the slope of the tangent line, right? We're taking Q and we're making it approach 0, meaning it's getting closer to P. So the slope of the tangent line is equal to the limit as H approaches 0 of our difference quotient right here, right? So we have f of x plus H minus f of x. Okay. All over H. So this right here is the slope of the tangent line. That's how we go from this, the slope of the secant line, to the slope of the tangent line. We take the limit of this. Because when we take the limit, we're saying, hey, we're going to take Q, make it really, 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 really close to P, so close that it's almost the same thing, but it's not equal, or it's not, but it's so close that it's basically the tangent line, all right? So that's the whole idea right there. And remember this right here, all right, the slope of the secant line, right, this was average rate of change. When you find the slope of the tangent line, this is considered instantaneous rate of change. Okay, so slope of the secant line is average rate of change. Slope of the tangent line is the instantaneous rate of change, right? We're finding the rate of change right at this point, what it is, okay? And we also know that the slope of the tangent line is instantaneous rate of change, and it's also the derivative, okay? Also the derivative. Right? So when you're finding the derivative, keep in mind, right, later, when you're finding the derivative, you're finding the slope of the tangent line, which is also considered the instantaneous rate of change. Okay, the instantaneous rate of change. Alright, so derivative, instantaneous rate of change, slope of the tangent line, they all mean the same thing. Okay, they all mean the same thing. Alright, let's recap some main ideas. So the slope, which is m is equal to y2 minus y1 over x2 minus x1, is the same thing as the slope of a secant line. Alright, same idea. So if we go back to our secant line right here, the one in green, remember we have two coordinates. The coordinates for P was x and f of x. The coordinates for Q was x plus h and f of x plus h, right? And when you throw them into the slope formula, you just ended up with this. Alright, so, and then if we simplify the x's here, the slope of the secant line is just f of x plus h minus f of x over h. Okay? So these two essentially mean the same thing. They are the same thing. Right? And this is known as the difference quotient. Right? If we subtract the x's here and cancel them out, you get over h. That's the difference quotient. Alright? Now the slope of a tangent line, that was when we took the idea that, okay, let's say we take P and we move, sorry, not P, but Q, we take Q and we move it really, really close to P. Very, very, very close, but it can never be equal, right? So as we do that, H is approaching 0, right? Whatever h is, or here this distance, as q starts getting closer to p, it starts decreasing to the point where it's almost 0. It can't be 0 because p and q cannot equal each other, because then we'll be dividing by 0. Right? So that idea is known as the limit. Right? So if we take the limit of the difference quotient right here, if we take the limit as h approaches 0, right, we get the instantaneous rate of change, right, which is also the slope of the tangent line. And as we'll learn, it is also the definition of the derivative. Right? So if this function is f of x, the derivative is represented as f prime of x, right, with this little kind of apostrophe to show that it is the derivative of f of x. Okay, so all these three, the slope of a tangent line, instantaneous rate of change, and the definition of the derivative, all right, is all the same thing. So the main thing you have to remember, the derivative is the slope of the tangent line. Right? The derivative is the slope of the tangent line. Okay?